Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at preparing nodes for Kubernetes and, well, specifically diving into the murky world of user access.
Yeah, which is, imagine you're an IT administrator, right? Your new intern just started. You run a single, seemingly harmless command to give them access, and suddenly half your production servers are deleted. Poof, just gone.
Oh, it is the absolute cold sweat nightmare of anyone working in infrastructure. Just the sheer panic of realizing you gave the wrong person the wrong keys.
And it happens way faster than you think.
Yeah.
So welcome to this deep dive. Today, we are really tearing into Kubernetes user access because, well, if you're listening to this, you probably already know the stakes.
Right, absolutely.
We're relying on a very specific, highly technical source document called CKA scenario-01.md to guide us. And for those familiar with the landscape, that CKA stands for Certified Kubernetes Administrator.
Yeah, and the scenario outlined in that source is just incredibly practical. It gives us the exact, precise steps for setting up a new administrative user, let's just call him John, on a freshly configured cluster.
Right.
But, this isn't just about passing a certification exam. If you're managing cloud infrastructure today, understanding this process is about fundamentally grasping how identity, cryptography, and permissions actually work under the hood.
Because if you don't understand the mechanics of how a system validates a user, you really can't protect that system from catastrophic security failures.
Exactly. You're flying blind.
So we're going to completely demystify this process today. We're going to follow the roadmap of John's digital identity, starting from absolute zero, building it the hard manual way, and then looking at the automated tools that can do it for us and the hidden dangers they carry.
Let's start with John. He's a new hire. He's sitting at his desk, drinking his coffee, waiting for access. Right now, to the Kubernetes cluster, John does not exist. He's just a ghost.
Which brings up the first major hurdle. According to the document, we have to build his digital identity entirely from scratch using cryptographic keys. But I have to stop right there, because that sounds crazy to anyone coming from traditional IT.
Oh, I know. It really does.
You're telling me this incredibly advanced orchestration platform doesn't have, like, a simple SQL table where I can just click Add User and type in John with a password. Why would they design it that way?
It's a fundamental architectural choice. Kubernetes just does not have a built-in user database. There is no user table in the Kube API.
Wait, none at all?
None. It relies entirely on external identities. It's built on a zero-trust philosophy where the platform itself doesn't want the liability of managing passwords. It expects you to bring your own validated identity, and in this specific scenario, it relies on X509 certificates.
Okay, so step one in our source document is generating a new private key for John. Let's visualize this. If John is applying for a highly secure corporate ID badge to get into our secret facility, generating this private key is basically him registering his unique biometric fingerprint, right?
You're on the right track, but let's push that analogy a bit further to really capture the cryptography. It's less like a fingerprint and more like John is forging his own uncopyable physical key right at his desk.
Okay.
And at the exact same time, he creates a specialized padlock that can only be opened by that specific key. He keeps the key, that is his private key, and he must guard it with his life. He hands over the padlock, which is his public key.
Ah, right, the magic of asymmetric cryptography.
Mm.
So he has his private key, and step two in the document is creating a certificate signing request, or a CSR.
Exactly. He packages that public padlock into a digital envelope along with a claim of identity. The CSR basically says, I am John, here's my padlock, please verify this so everyone knows it's really mine.
So it's basically the official paper application form for his ID badge.
Yes.
Exactly, yeah.
But I'm looking at steps 3 and 4 in the document, and I am genuinely lost here. We have the CSR file. It already exists on John's machine, but the instructions say we have to run a command to encode that CSR into a base 64 string.
Right.
And then we have to create a YAML file, specifically named john-csr.yaml, and take that massive string of gibberish and drop it directly inside a field called spec.request.
Yeah, that's the process.
Why on earth are we doing this extra cryptographic gymnastics routine just to cram text into a YAML document? Like, why can't Kubernetes just read the raw CSR file directly like any normal software?
That is the exact point where a lot of people get tripped up. It comes down to how systems communicate and parse data over a network. A certificate signing request, in its raw form, is a binary file.
Okay.
It's full of complex, non-printable characters that represent the dense mathematical data of those cryptographic keys.
Right, so it's not meant for human eyes at all. Not even a little bit. But the Kube API, the central nervous system of Kubernetes, communicates using RESTful APIs, which expect structured, plain-text payloads like JSON or YAML. And YAML is meant to be human-readable.
So if you put binary in there.
If you try to force-feed raw, unpredictable binary data into a text-based YAML file, the YAML parser will completely choke. It might misinterpret a random binary character as a line break or an end-of-file signal, and the whole request just shatters.
Oh, I see. So the base64 encoding is essentially a translator.
Precisely. Base64 is an encoding scheme that takes that volatile binary data and translates it into a standard, safe alphabet of 64 plain text characters, just standard letters and numbers.
It's brilliant.
By encoding the CSR into Base64, we ensure that the YAML file remains perfectly structured. We're safely packaging a fragile binary application inside a sturdy text envelope so it actually survives the journey to the Kube API.
That makes perfect sense. The parser doesn't break because it just sees standard text. Okay, so we've packed John's identity into this YAML envelope. But an application is totally useless unless someone actually looks at it and approves it, right? What happens when we finally submit this to the cluster?
Well, this is where the bureaucracy begins. You use a tool called Kubectl to apply the manifest. Once that YAML file is applied, the request is sitting inside the Kubernetes system, but it's in a pending state.
So it's just sitting in the inbox on the security guard's desk.
Exactly. The system doesn't inherently trust it yet. The next step mandated by the source is that the CSR must be formally approved. An existing administrator has to manually review this request and issue a specific kubectl approval command. This ensures a strict separation of duties.
And once it's approved by that admin,
the system springs into action. The cluster's internal certificate authority takes John's public padlock, signs it with the master company seal, and generates the final .crt file, the certificate.
So getting that .crt file is like the security guard finally stamping John's application approved and printing out the actual physical ID badge.
Yes.
John now has the badge. He's officially recognized by the system.
He is recognized, yes. The cryptography checks out perfectly.
But wait. Looking at the document, we aren't done. The very next step after generating the certificate is creating something called a ClusterRoleBinding to put John in the administrator user group.
Right.
If the system just verified his fingerprint, stamped his application, and printed his badge, why do we need a role binding? Didn't we already say yes to him? Why can't he just walk into the cluster and do his job?
This highlights one of the most critical security concepts in all of computing, and it's something every listener needs to internalize. It's the absolute firewall between authentication and authorization.
Okay, lay that out for us. What's the difference?
Everything we just did, generating the key, submitting the CSR in Base64, manually approving it, and minting the certificate file that was purely authentication. Authentication just proves identity. It answers one simple question: are you really John? The cluster now mathematically agrees, yes, this digital signature belongs to John.
Right.
But authorization is an entirely different beast. Authorization answers the question, what is John actually allowed to do?
I see. So it's like having a passport. My passport undeniably proves who I am, gets me through the front doors of the airport, but just because I have a passport doesn't mean I'm allowed to walk out onto the tarmac, hijack a 747, and fly to Hawaii.
That is a fantastic way to look at it. But let's take it even further, because Kubernetes is a zero-trust airport.
Okay.
In Kubernetes, your passport doesn't even let you look at the departure screens. By default, John has absolutely zero permissions. He can authenticate, but if he tries to view any resources, the Kube API will outright reject him.
Wow, zero permissions by default.
Exactly. That's why the source requires a cluster role binding. We're taking John's validated identity and we are binding it to a set of rules in this case, the pre-existing administrator role. We are actively granting him his powers.
That distinction is brilliant. Authentication proves you exist. Authorization gives you the power to act.
You got it.
Okay, so John is authenticated, and thanks to the role binding, he's authorized as an admin. But he's still just sitting at his laptop. He has his admin badge, and his permissions are logged in the system, but he still needs to know how to actually connect to the infrastructure, right?
Correct. The source document outlines the final manual steps to make John operational locally. His user credentials, that private key he generated, and the newly signed certificate badge must be configured in a local file called .kube/config.
Right. I've always thought of the kubeconfig file as basically a personalized GPS device for the developer.
It is, but it's a bit more involved than a standard GPS. Think of it less like a navigation app on your phone and more like a highly specialized, high-security company vehicle.
Oh, I like that.
Yeah, so it has the GPS coordinates to the cluster pre-programmed into the dashboard, but it also has a specialized ignition switch. That vehicle will not even turn on unless John inserts his specific private key and his newly minted badge into the console.
That makes a lot of sense. And the document notes that the context must be set. It assumes the cluster we are targeting is named Kind Kuka.
Right.
So we are telling this company vehicle exactly which building to drive to because in the real world, John might have access to a dozen different clusters.
Exactly. The context binds the user, the cluster address, and the namespace together. And then the absolute final step of this grueling manual process is testing the connection using kubectl.
Right.
Verifying that the vehicle actually drives to the Kind Kuka building and the badge actually opens the front door.
But stepping back and looking at this whole process, it is an incredibly tedious, error-prone dance. We generated cryptographic keys, we dealt with binary-to-text base64 encoding, we wrote YAML files, we waited for a human to manually approve the request, we created role bindings, and we manually modified configuration files. Just for John, one guy.
It's a massive amount of overhead.
If a tech enterprise has 500 or 1,000 developers, are they really doing this base64 YAML dance for every single person who joins the company? That seems absolutely impossible to scale.
Oh, it is impossible to scale. If you were managing hundreds of developers, you aren't doing this.
Okay, thank God.
Right. In massive enterprise environments, they integrate Kubernetes with external identity providers using protocols like OpenID Connect or OIDC. They tie the cluster directly into the company's existing single sign-on systems like Active Directory or Okta.
Okay.
So when John logs into his company email, he gets a token that Kubernetes can instantly verify.
Okay, so this manual way is really for the ground floor.
Yes. For smaller clusters or for the initial bootstrapping of cluster administrators before SSO is set up, you still need ways to provision access locally. And because doing it by hand is so painful, the creators of Kubernetes provided some automated shortcuts.
Which brings us to the final section of our source document, the easy button. Our source material provides an alternative for admins using a tool called kubeadm to shortcut this massive process.
That's right. According to the document, you can use a specific command. Kubeadm kubeconfig user. This one command acts like a magical wizard behind the curtain.
Oh, wow.
Yeah, it automatically generates the private key, creates the certificate signing request, gets it signed by the internal CA, and spits out a fully formed, ready-to-use kubeconfig file containing those signed credentials.
So it skips the YAML entirely. It skips the base64 translation. It basically just hands you the pre-programmed company vehicle with the keys already in the ignition.
It does. It's incredibly convenient. But as we know, shortcuts in infrastructure always come with deep security considerations. You have to tell kubeadm exactly what kind of permissions this new user should have, and the source document outlines two very distinct options for creating an admin using this tool.
Let's look at option 1. The document calls this creating a super admin, and it explicitly states that this option bypasses role-based access control RBAC entirely.
Yep.
It says it gives the user unrestricted super user access by joining them to a group called system::masters. To me, this sounds exactly like a God mode cheat code in a video game. You just walk through walls, you have infinite ammo, the actual rules of the game's physics no longer apply to you.
That is not an exaggeration. That is precisely what it is. Now, option 2 is slightly different. The document calls option 2 an RBAC-based admin.
Yep.
Interestingly, this is the default behavior if you just run the kubeadm command without special flags. If you use this option, it joins the user to a group called kubeadm::clusteradmins, which is bound to the standard cluster admin role.
Okay, so if option 1 is the God mode cheat code where the laws of physics don't apply, option 2 is more like giving someone, the master, physical keys to every door in the building.
Right.
You can open any door, you can go into any secure room, but you're still subject to the physical laws of the building. You leave footprints, and more importantly, the security cameras are still on and tracking your movements.
That is a crucial distinction. Option 2 still utilizes role-based access control. John would have immense sprawling power, but that power is explicitly defined by a set of rules. His actions are evaluated against those rules every single time he makes a request to the Kube API.
Which is good for auditing.
Exactly. And if an auditor needs to, they can modify those rules to restrict him later.
But I'm seriously hung up on option 1. If option 1, this system::masters group, bypasses all RBAC controls entirely, why would that even be an option? Shouldn't a highly secure system always force some level of rules? Why does Kubernetes even have a God mode built into the source code?
It sounds terrifying, but System: Masters isn't just an administrative group, it's a hard-coded failsafe. Imagine this scenario. What happens if a junior developer accidentally writes an RBAC rule that denies access to absolutely everyone?
Oh, yeah.
Or what if someone accidentally deletes the cluster admin role entirely?
You would be completely locked out of your own house. The cluster would just sit there, humming along, running workloads, and nobody on Earth could talk to it or fix it.
Exactly. You would have a perfectly healthy cluster that is entirely orphaned. System: Masters exists to prevent that catastrophic lockout.
Okay, that makes sense.
The Kube API is hard-coded at a foundational level to look at any certificate bearing the System: Masters group and say, I am not even going to check the RBAC rules for you. You have absolute, unconditional overriding authority.
It's the break class in case of emergency failsafe.
Okay, that makes complete sense from a disaster recovery standpoint. But it also means it's incredibly dangerous if misused. Beyond dangerous. That is exactly why the default for kubeADM is option 2. You want your daily administrators bound by RBAC so their actions can be audited, tracked, and restricted if necessary. You only ever use option 1 when you absolutely need an untethered super user to salvage a broken system.
And the source adds one final, very important catch here. We've talked extensively about these kubeADM shortcuts, but the document explicitly states, quote, for non-admin users, use the standard process outlined above.
Right.
Meaning, if you just want to add a read-only user or a developer who only has access to one specific namespace, the easy button does not apply. You absolutely must go back to the manual process. The private key, the CSR object, the base 64 text translation, the YAML, and the manual approval.
Right, because kubeADM is fundamentally a cluster bootstrapping tool. It's designed to help you stand up the infrastructure and get the initial foundational admins logged in so they can build the rest of the house.
Right, it gets the ball rolling.
Exactly. It is not designed to be your daily user management system. For granular, specific day-to-day access, you have to do the work. You have to understand the cryptography and the bureaucracy.
So let's pull all of this together. We just took an incredible journey. We started with a brand new, empty cluster and a user named John, who is nothing but a ghost. We walked through the painstaking process of handcrafting a digital identity for him.
Yeah, we did.
We generated a private key. We created a certificate signing request application. We learned exactly why we had to translate that volatile binary data into plain text base 64 just so a YAML file could safely carry it to the Kube API.
And then we navigated the system's bureaucracy. We applied the manifest. An existing administrator manually approved it to ensure separation of duties, and we extracted the final certificate badge.
But having the badge wasn't enough. We dove into the critical firewall between authentication and authorization, setting up a ClusterRoleBinding so John wasn't just recognized, but actually had the power to do his job. We configured his kubeconfig file like a high-security vehicle, pointing him to the Keka cluster.
And finally, we looked at how automated tools like kubeADM can shortcut that entire process for bootstrapping while carrying the heavy responsibility of choosing between RBAC-bound administrative roles and the absolute unrestricted power of the System: Masters failsafe.
It is a massive amount of architecture to take in. But honestly, walking through the manual process step by step really pulls back the curtain on how security actually functions at a mathematical level.
If you're the admin listening to this right now, that is the real takeaway. Knowledge is most valuable when it's understood at its foundations. Understanding the manual process of the hard way is what makes you a true infrastructure professional.
Absolutely.
Anyone can search Google for a tutorial and copy-paste a kubeADM command to press the easy button. But when something breaks, or when a parser fails, or when you need to design a custom security policy from scratch, pressing the easy button just isn't enough. You have to know exactly what that button is doing behind the scenes. You have to know how the cryptography locks and unlocks the doors.
You have to know how to read the raw data, even when the automated tools fail. Because when they do fail, you are the final line of defense.
Exactly.
Which brings me to a final thought I want to leave you with. Something for you to mull over long after this deep dive is done. We discovered in the source document that the System: Masters group is a hard-coded failsafe. It completely bypasses all role-based access control. It operates entirely outside the laws of the Kubernetes universe.
Right.
So I want you to think about the security posture of your own infrastructure right now. If that group essentially ignores all the rules, How secure is any cluster, really, if a malicious actor figures out a clever way to sneak an account into that specific group? It is a sobering reminder that in cloud architecture, sometimes the ultimate backdoor isn't a clever hack. It's built right into the system by design.
It certainly makes you want to go audit your ClusterRoleBindings this afternoon, doesn't it?
It really does. Thank you for joining us on this journey into the depths of cluster security. We will see you on the next deep dive.